Welcome back to PV Online. And today we're going to look at both elastic and inelastic collisions dealing with conservation of momentum. So we have this example right here. We have two objects and they're both moving, and we have the information about them before the collision and we have it after the collision. And what we want to do is we want to find out that unknown variable. So in this case, I want to find out the final velocity of the 6-kilogram object. All right, so in order to do this, since we have two objects, we need to identify them. And the way I want to do that is I'm going to call him M1, and I'm going to call the 4-kilogram object M2. Ah, that was kind of sloppy. This is going to be M1, and this guy will be M2. All right, so we have our information, and we know that momentum is going to be conserved. That means the initial momentum is going to equal the final momentum. This is an elastic collision, and for our purposes, we're going to have the system is isolated, so the total momentum is going to be conserved. So we're going to use the relationship that M1 V1 initial plus M2 V2 initial is going to equal M1 V1 final plus M2 V2 final. All I'm doing is summing up the momentums of all the objects before the collision and after the collision. So let's start plugging in some values. And we know that M1 has a value of 6 kilograms. V1 initial, this is before the collision, is 10 meters per second, plus M2, which we said was 4 kilograms, and V2 initial is also 4 meters per second. That's going to equal M1, which we said was 6. I don't know the final velocity of object 1, so I'm going to leave that as V1F. The subscripts are just telling us which object so we can keep track. M2 we said was 4 kilograms, and V2 final is 10. All right, now all we have to do is solve for V1 final. 6 times 10 is 60, plus 4 times 4, which is 16, equals 6 V1 final, that's what I'm looking for, plus 4 times 10, which is 40. All right, we add these two together, that gives me 76 equals 6 V1 final plus 40. Dealing with order of operations, I now have to subtract 40 from both sides. That's going to give me 36 equals 6 V1 final. I divide both sides by 6. That gives me V1 final equals 6 meters per second. So look at what happens. During this collision, the smaller object starts moving off faster, causing the larger object to slow down a little bit. All right, let's take a look at another example. Now in this example, we have the two objects. Again, I'm going to refer to this one as M1 and this guy over here is M2. But how is this collision different than the one before? And it's different because this is an inelastic collision, which means they stick together. Now momentum is still going to be conserved, meaning that my initial momentum is going to equal my final momentum. So I can add up the momentums of both object 1 and object 2. But this time when they stick together, their final velocities will be the same. And since the final velocity is going to be the same, I can just add up their masses right here. I'm factoring out the final velocity. And my equation now looks like this because they both have the same final velocity. All right, M1 had a value of 4. V1 initial had a value of 8. M2 had a value of 2. V2 initial had a value of 5. Equals M1, which is 4. M2, which is the mass, is 2. V final. All right, 4 times 8 is 32. Plus 2 times 5, which is 10. Equals 4 plus 2, 6 V final. 32 plus 2 is 42. Equals 6 V final. In order to solve for V final, I divide both sides by 6, and when I do that, I get a final velocity of 7 meters per second. So this guy is going to take off to the right at 7 meters per second. So you can see how the 2 kilogram object sped up a little bit, but the 4 kilogram object slowed down. The momentum had to be conserved. And now we're going to look at our final problem. Now, first things first, what kind of collision is this? Is this an elastic or an inelastic? They're not sticking together, which makes it an elastic collision. Momentum is going to be conserved, so my initial momentum is going to equal my final momentum. But look at what's different with this guy. And you can see how the 8 meters per second is moving to the right, but the 2 kilogram object is moving to the left. Momentum is a vector, and since it's a vector, that means direction counts. And mathematically, what do we do to show that the direction is to the left? We include a negative sign. So since it's an elastic collision, I'm going to say M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. These are just our momentum terms, mass times velocity. I'm using the subscripts because we have so many different ones, I have to keep track of them. So I'm going to take 3 times 8 plus 2 times negative 6. Remember, that's going in the opposite direction. Equals M1, which is 3. But look at the direction that it's going. It's going to the left, making it a negative 2. Plus M2, which was 2, times V2 final. 3 times 8 is 24, minus 12, because 2 times negative 6 is negative 12, equals negative 6 plus 2 V2 final. All right, 24 minus 12 is going to give me 12, equals negative 6 plus 2 V2 final. I have to add 6 to both sides, so that's going to be 18 equals 2 V2 final. V2 final then is going to be 9. All right, the big idea here, momentum is conserved. How much momentum you have before the collision is going to equal how much afterwards. Keep in mind it's a vector, direction counts. And make sure you can identify elastic and inelastic collisions. All right, we'll see you next time.